Look up at the night sky, and it's easy to feel a sense of peace. The stars seem constant, silent, and serene. But out there, hidden in the vast darkness, cosmic chaos is unfolding on an unimaginable scale. Almost 1,000 years ago, observers on Earth witnessed a new star blazing brightly in the sky, so brilliant it was visible even during the day. What they were seeing was the violent death of a star, a supernova explosion that would leave behind one of the most mesmerizing and mysterious objects in our galaxy, the Crab Nebula. This cloud of stellar debris isn't just a static monument to that ancient cataclysm. It's a dynamic, churning, and deeply strange cosmic phenomenon that continues to defy our understanding of the universe. At the heart of this nebula lies a pulsar, spinning furiously and firing beams of radiation across space like a celestial lighthouse. But that's just the beginning. The Crab Nebula is packed with bizarre behaviors that challenge everything we think we know about physics, from its rapidly expanding filaments of glowing gas to its mysterious high-energy emissions that shouldn't be possible. It's a place where magnetic fields twist into impossible shapes, where particles are accelerated to nearly the speed of light, and where the laws of nature seem to warp in ways that leave even the most seasoned astronomers in awe. This isn't just a cloud of dust and gas. It's a cosmic laboratory brimming with secrets waiting to be uncovered. In this video, we're going to explore 30 of the strangest, most mind-bending phenomena hidden within the Crab Nebula. We'll dive into its pulsing core, trace the paths of its shimmering tendrils, and unpack the riddles that have puzzled scientists for decades. This is a journey to the edge of understanding, a voyage into one of the most spectacular and bewildering regions of space ever observed. So settle in and open your mind. What you're about to discover will forever change how you see the stars. And right at the heart of that chaos, driving the entire spectacular display, is the engine of the Crab Nebula itself, a city-sized spinning star known as the Crab Pulsar. Imagine taking an object with more mass than our Sun and crushing it down into a sphere only about the size of a large city. The forces at play are so unimaginable that the very atomic structure of matter collapses, creating a super-dense orb made almost entirely of neutrons. Now set that incredibly dense sphere spinning, not slowly like a planet, but with a ferocious, dizzying velocity. The Crab Pulsar completes a full rotation roughly 30 times every single second. To put that into a human perspective, if you were standing on its surface, which you absolutely could not survive, you would be whipping around at nearly a tenth of the speed of light. This insane spin is a direct consequence of the law of conservation of angular momentum. Think of an ice skater pulling their arms in to spin faster. The original star was already rotating, but when its core collapsed in that supernova explosion almost 1,000 years ago, it pulled all of that rotational energy into an infinitely smaller space, causing its spin rate to skyrocket to these incredible speeds. But the spin is only half of what makes this object so extraordinary. It also possesses a magnetic field of truly mind-boggling strength, a quadrillion times more powerful than Earth's magnetic field. This combination of rapid rotation and an ultra-powerful magnetic field is what transforms this dead star into a pulsar. The magnetic field axis isn't aligned with the star's rotation axis. So as the star spins, these powerful magnetic poles whip around, accelerating charged particles and funneling them outward in two intense beams from the magnetic poles. These beams are not just made of light, they contain every form of energy across the electromagnetic spectrum, from radio waves to the most powerful gamma rays. And because the star is spinning, these beams sweep across space like the beams of a cosmic lighthouse. From our vantage point on Earth, we see a flash of radiation every time one of those beams points in our direction, resulting in a pulse of light precisely 30 times a second. This clock-like regularity is so dependable that astronomers once used the Crab Pulsar's timing to help calibrate their instruments. This pulsar isn't just a silent beacon, it is the primary power source for the entire nebula. It continuously floods its surroundings with a violent stellar wind of radiation and high-energy particles. This wind injects immense energy into the expanding cloud of gas and dust from the supernova, causing it to glow across all wavelengths and continue pushing outward at over 1,000 miles per second. Without the pulsar's constant energy input, the Crab Nebula would have faded into darkness long ago. It is a stellar corpse, yes, but it is far from dead. It is a dynamo, a cosmic generator that brings the echo of a 1,000-year-old explosion to life every single day. But the Crab Pulsar isn't the only source of baffling energy in this system. Just when astronomers thought they had a handle on this cosmic powerhouse, the nebula presented them with a mystery that, quite literally, defies the laws of physics. For years, the Crab was considered a steady, reliable source of light. A calibration tool so stable it was nicknamed the standard candle of high-energy astronomy. That all changed in 2011 when the Fermi Gamma-Ray Space Telescope detected something impossible, a series of massive gamma-ray flares erupting from the nebula. These aren't just minor fluctuations, these flares are monumental outbursts of energy, so powerful that they can temporarily make the nebula 5 times brighter in gamma-ray light, and they can last for days. To put that into perspective for a brief period, these random flares outshine the combined output of the entire nebula and its hyperactive pulsar. The energy required for such an event is staggering, and according to our established models of particle physics and astrophysics, it simply shouldn't be happening. In a system that's supposed to be stable and well understood, these flares are like a quiet, predictable library suddenly and without warning, erupting with the force of a volcanic explosion. The central puzzle is the speed of the particles involved. Gamma rays are the most energetic form of light in the universe, and producing them requires accelerating subatomic particles to velocities infinitesimally close to the speed of light. Our best theories, including those that beautifully explain the pulsar's behavior, suggest there's a fundamental limit to how fast particles can be accelerated within the nebula's magnetic fields. It's a cosmic speed limit set by the balance of energy and the structure of space itself. Yet, these flares are screaming past that limit. The particles responsible for this light are moving faster than our physics says they possibly can, as if they've found a hidden loophole in the laws of nature. So what cosmic engine could possibly be responsible? Astronomers are playing detective with the universe's most extreme events. The leading suspect is a process called magnetic reconnection. Imagine the nebula's magnetic field lines, which are incredibly twisted and complex, suddenly snapping and reorganizing themselves. This sudden reconfiguration can release an enormous amount of stored energy all at once, like an over-tightened rubber band finally breaking and snapping forward, potentially launching particles to these impossible speeds in a violent, concentrated burst. Other theories point to instabilities in the pulsar's powerful wind or even interactions within the nebula's dusty filaments that create perfect, temporary particle accelerators far more efficient than anything we can build on Earth. To solve this, scientists are on constant watch, using an array of telescopes from radio observatories to X-ray satellites like Chandra, all trained on the Crab, hoping to catch a flare in the act. Each new detection is a precious data point, a clue that could help us rewrite our understanding of high-energy physics. This isn't just an academic exercise. Cracking this code could reveal new fundamental principles about how energy works throughout the cosmos, principles that might apply to quasars, supernova, and other extreme celestial events. The Crab Nebula, once a textbook example of a settled science, has become a living lesson in cosmic humility, reminding us that the universe always has new secrets to reveal. And adding to that unpredictable gamma-ray fury, the Crab Nebula presents us with another visual marvel that is equally deceptive in its gentle appearance, the enigmatic structures known simply as the wisps. If you've ever seen a long-exposure photograph of the crab, you might have noticed these faint, ethereal tendrils curling through the nebula's heart. They look almost like delicate brushstrokes on a cosmic canvas, but this serene appearance is a complete illusion. These are not passive clouds of dust. They are violent, ultra-relativistic shock waves, and they are moving at a significant fraction of the speed of light. These wisps are a direct and visible consequence of the pulsar's power. Remember that incredible pulsar wind, the torrent of radiation and particles constantly streaming from the central neutron star. That wind doesn't just smoothly pour into the nebula. It slams into the slower-moving shell of gas and dust that was ejected during the supernova explosion itself. It's a cosmic traffic jam of epic proportions, where material moving at nearly the speed of light collides with material expanding at a mere few thousand miles per second. The result is a series of standing shock waves that form at this collision boundary, and it is these shocks that we see glowing as the famous wisps. The real mystery, and what makes them so strange, isn't just their existence but their behavior. Through meticulous time-lapse observations, primarily with the Hubble Space Telescope, astronomers have watched these features undergo dramatic and unexpected transformations. A wisp will suddenly brighten, then fade away. Another will appear almost out of nowhere, while others shift their position or change their shape in a matter of days. This is not the slow, stately dance of gas clouds we see in other nebulae. This is a frenetic, almost frantic display of activity. This unpredictable motion challenges our best models of how magnetized fluids behave in space, a field known as magnetohydrodynamics. The wisps seem to be governed by incredibly complex and unstable interactions between the pulsar wind's powerful magnetic field and the ionized gas of the nebula. It's a constant tug of war where magnetic pressure and gas pressure fluctuate, causing the shock front to ripple, buckle, and reorganize itself in ways that are exceptionally difficult to predict or replicate in computer simulations. Watching the wisps is like watching a live broadcast of a fundamental physical process that we are still struggling to fully comprehend. Yet, for all their strangeness, these dynamic features are crucial. They are not merely a side show, they are one of the primary mechanisms by which the pulsar's energy is transferred to the wider nebula. As the shock waves plow through the surrounding material, they transfer energy and heat the gas, causing it to glow across the entire electromagnetic spectrum. They also act as colossal particle accelerators, further boosting electrons and other particles to extreme energies. In a very real sense, the ever-shifting pattern of the wisps is a visible map of the ongoing power struggle at the heart of the crab. A continuous reshaping driven by the raw, untamed energy of a dead star. While the inner regions churn with the pulsar's violent energy, the outer edges of the Crab Nebula are engaged in their own breathtaking race against time and space. The entire structure, that magnificent web of glowing filaments, is expanding outward at an average velocity of about 1,500 kilometers per second. To put that incomprehensible speed into a human context, an object moving that fast could travel from the Earth to the Moon in a little over 4 minutes. This is the momentum from the original supernova explosion still carrying the stellar debris outward nearly a millennium later. But this expansion holds a strange and critical clue. It is profoundly uneven. If the nebula were a perfectly symmetric balloon inflating in the vacuum of space, we would expect every part of it to move outward at the same relentless pace. Yet, detailed observations reveal a far more chaotic reality. Certain sections of the nebula's shell are surging forward significantly faster than others, while some regions seem to be lagging behind or even changing direction. This isn't a clean, uniform expansion. It's a messy, lopsided, and still evolving aftermath of a cosmic catastrophe. The question is, what forces are pulling the strings on this chaotic dance? Astronomers have two primary suspects for this strange acceleration. The first points outward to the environment surrounding the nebula. Space is not a perfect vacuum. It's filled with a thin soup of gas and dust known as the interstellar medium. As the supernova blast wave plows into this material, it doesn't encounter a uniform resistance. It's like running through a field of tall grass where some patches are thick and tangled and others are clear. The leading edges of the nebula that hit denser clumps of interstellar material will naturally slow down, while sections expanding into clearer voids can race ahead unimpeded, creating those dramatic speed differences. The second suspect points inward to the very nature of the explosion itself. The death of that massive star 1,000 years ago was likely not a perfectly symmetrical event. Modern supernova models suggest these explosions can be inherently lopsided, with shock waves and ejected material jetting out much more forcefully in certain directions than others. The kick from the newborn neutron star itself could have been off-center, sending it recoiling through the debris and further stirring the pot. The uneven expansion we see today could very well be a frozen-in snapshot of that original asymmetry, a testament to the chaotic violence of the star's final moments. Measuring this motion with such precision is a triumph of long-term astronomical observation. How do you track the growth of an object that is 6,500 light-years away? The method is as elegant as it is simple. Compare old photographs with new ones. The first detailed photographic plates of the Crab Nebula were taken in the early 20th century. By taking modern, high-resolution images from telescopes like Hubble and comparing them directly to those century-old portraits, astronomers can detect the slightest shift in the position of individual filaments. They are essentially creating a multi-decade time lapse of the nebula's evolution. By measuring how far a specific knot of gas has moved over that known period of time, they can calculate its exact velocity across our line of sight. This isn't just about charting motion, it's a form of cosmic archaeology. By reverse engineering the expansion, tracing all the streaming filaments backward like a movie in rewind, astronomers can pinpoint the exact date when all this matter was in one place, the moment of the supernova explosion. This calculated date aligns almost perfectly with the historical records from the year 1054, when Chinese and Arab astronomers documented the appearance of a guest star bright enough to be seen in daylight. The expansion speed, therefore, does more than just reveal physics. It connects our modern scientific inquiry directly to an event witnessed by human eyes 1,000 years ago, creating a tangible link between ancient astronomy and our ongoing quest to understand the universe's most dynamic processes. But the visible turmoil of the expanding filaments and the shocking gamma-ray flares are only part of the crab's mystique. To uncover its deeper secrets, we have to look at it in a different kind of light our eyes cannot see. When astronomers point powerful infrared telescopes like Spitzer and now the James Webb Space Telescope toward the crab, they encounter a phenomenon that, while less flashy than a violent flare, is just as puzzling: an infrared excess. In simple terms, the nebula is glowing far more brightly in infrared light than any of our models say it should. It's as if we've carefully calculated the output of every known light bulb in a city, only to discover the entire sky is still glowing with an unknown, pervasive warmth. This mysterious infrared glow is widely believed to come from dust, not unlike the dust you might find on a bookshelf, but in this case, it's cosmic dust, microscopic grains of carbon and silicate minerals that were forged in the atmosphere of the original star and then blasted into space during its supernova death. The theory is straightforward enough. The intense radiation from the pulsar at the nebula's heart should heat these dust grains, causing them to re-radiate that energy as infrared light. The problem is that the math doesn't add up. The amount of infrared light we see and the way it's distributed across the nebula simply doesn't match the predictions based on the amount of dust we think should be there and the known energy output of the pulsar. So where is all this extra infrared light coming from? One compelling idea is that the composition of the dust itself might be far stranger than we assumed. Perhaps the extreme conditions within the nebula have created exotic forms of matter or unusual chemical compounds that absorb and emit radiation in ways our current dust models don't account for. Another fascinating possibility is that we are witnessing the continuous creation of new dust. The turbulent environment, with its powerful shock waves and intense radiation, could be constantly shattering larger grains into smaller fragments or even assembling new, tiny particles from available gas. This ongoing process would create a population of very small, very hot grains that could collectively produce a much stronger infrared signal than a static cloud of older, more established dust. This is where the incredible power of the James Webb Space Telescope comes into play. Its unparalleled infrared resolution allows it to do more than just confirm the excess. It can map it with breathtaking detail. By studying the specific wavelengths of this infrared light, JWST can act like a cosmic geologist, identifying the precise chemical fingerprints of the materials responsible. It can distinguish between different types of carbon grains, spot the signatures of silicates, and potentially even identify entirely new compounds. Furthermore, by comparing JWST's sharp new images with older data, astronomers might be able to see if the infrared bright regions are moving or changing, telling us if this dust is a permanent feature or a dynamic, evolving component of the nebula. Solving the infrared excess puzzle is about more than just accounting for missing light. It gets to the very heart of the life cycle of matter in the universe. Supernova are the primary factories that create and distribute heavy elements, the very elements that go on to form planets and indeed life itself. Understanding how much dust survives the violent aftermath of a supernova and what forms that dust takes is crucial to understanding how the universe builds new solar systems. The Crab Nebula's mysterious infrared glow is a direct message from that cycle of cosmic death and rebirth, and we are only just beginning to learn how to read it. Yet within that expanding chaos and the strange infrared glow, the Crab Nebula still manages to create pockets of near-perfect order. One of the most striking examples is a feature astronomers have nicknamed the anvil. Located deep within the nebula's inner regions, this structure stands out with a stark, almost architectural clarity. It consists of a long, narrow base that extends outward, culminating in a bright, compact, and remarkably flat cap. The overall shape is uncannily like a blacksmith's tool left lying in the cosmos, a hammer poised to strike against the anvil of space itself. What makes the anvil so strange isn't just its appearance, but its very existence. This is a region of incredible stability and symmetry, a calm and ordered form that seems to defy the frantic, violent turmoil that defines its surroundings. All around it, the wisps ripple and shift at near light speeds, magnetic fields tangle and snap, and high-energy particles rage in a relentless storm. In the midst of this astrophysical hurricane, the anvil maintains its defined shape, a testament to a powerful, unseen force that is somehow holding it together. This force is the pulsar wind itself. The anvil is not a static sculpture. It is a dynamic structure, continuously forged and maintained by the immense pressure of the particles and radiation screaming outward from the central neutron star. Think of it as a cosmic windsock. On a windy day, a windsock inflates and points steadily in the direction the air is moving, its shape defined by the constant pressure of the flow. The anvil operates on a similar principle, but with unimaginably powerful forces. It is essentially a bubble of compressed gas and magnetic field lines, inflated and sculpted by the pulsar wind into its distinctive form. The stability of its shape tells us something crucial about the wind. Its direction and intensity in that specific region must be remarkably consistent. For the anvil to persist, the pulsar wind must be striking that area with a steady, focused beam, much like a blowtorch heating a single spot on a piece of metal. The magnetic fields trapped within this structure are forced into alignment by this relentless flow, creating a rigid skeleton that helps the anvil keep its form against the buffeting chaos of the surrounding nebula. It's a delicate balance, a standing wave in a torrent of energy, and its continued existence is a direct measurement of the pulsar's unwavering power. Studying features like the anvil gives astronomers a unique laboratory to understand how complex structures emerge in extreme environments. It shows us that even within apparent chaos, there can be pockets of order governed by simple, powerful physical principles. The stability of the anvil provides a fixed point against which we can measure the faster-moving, more erratic wisps and filaments, helping us to calibrate our models of the incredible forces at work. It is a cosmic anchor, reminding us that even in the aftermath of a stellar explosion, the universe has a tendency to create moments of breathtakingly precise and beautiful structure. Moving inward from the structured calm of features like the anvil, we find a region of even more intense and unpredictable activity. Encircling the Crab Pulsar itself is a shimmering, dynamic crown of high-energy light known as the variable X-ray halo. This isn't a permanent, solid structure. It's a constantly shifting glow of X-ray emission that pulses, brightens, fades, and changes its very size on a timescale of just days or weeks. If the pulsar is the engine, then this halo is the visible and ever-changing exhaust plume, a direct and real-time readout of the immense power flowing from the neutron star and its chaotic struggle with the surrounding nebula. The Chandra X-ray Observatory has been instrumental in documenting this bizarre behavior. Its sharp X-ray vision allows it to see the halo not as a blurry cloud, but as a structured entity with distinct rings and layers that expand outward from the central source. The truly strange part is watching time-lapse sequences from Chandra. They reveal the halo's rings billowing outward like smoke rings from a sudden explosion, only to then contract or dissipate entirely, replaced by new structures forming closer to the pulsar. This is not a slow, stately expansion. It's a fitful, breathing, almost living phenomenon. So what drives this incredible variability? The primary culprit is believed to be the pulsar wind itself, that relentless torrent of radiation and particles flowing from the neutron star. But this wind is not a smooth, constant stream. It's inherently gusty and unstable, with its power and density fluctuating as the complex physics of the pulsar's magnetosphere plays out. Think of it like trying to force water through a hose that is itself kinking and unkinking randomly. The flow that comes out the other end will be irregular and pulsing. These changes in the wind's intensity directly impact the halo, causing it to brighten as a surge of particles hits it or to fade during a momentary lull. The other major player is the nebula's own magnetic field, which acts as a cage for this energy. The pulsar wind is loaded with its own magnetic field, and as it slams into the nebula, these field lines become tangled and compressed at the shock front. This creates a powerful barrier, a magnetic bottle that traps the high-energy particles, forcing them to whirl around in turbulent loops and emit the X-rays we see as the halo. When the magnetic field configuration suddenly shifts or undergoes a reconnection event, that same snapping process thought to cause the gamma-ray flares, it can temporarily change the size and shape of this bottle, allowing particles to escape faster or confining them more tightly, which we then observe as the halo growing or shrinking. This makes the variable halo far more than just a pretty light show. It is a crucial diagnostic tool. By carefully measuring how the X-ray emission changes, astronomers can effectively take the temperature and measure the pressure of the pulsar wind in a way they can't do directly. The brightness of the halo tells them about the density of particles, while its size and expansion speed reveal the strength of the confining magnetic pressure from the nebula. It's a natural laboratory for studying high-energy plasma physics, allowing us to witness how energy and magnetic fields interact in an environment far more extreme than anything we could ever recreate on Earth. Each fluctuation is a piece of data, helping us build a more complete picture of the incredible forces that continue to shape this 1,000-year-old explosion. Yet even the chaotic dance of the X-ray halo must eventually interact with the larger structures of the nebula, and some of the most fascinating of these are the small, intensely bright islands of matter known simply as the knots. If you look closely at a high-resolution image of the crab, you'll notice countless tiny, glowing specks scattered throughout its filamentary network. These aren't random pixels or camera noise, they are dense, compact clumps of gas, each one a surviving fragment of the star's own atmosphere, blasted into space during the supernova and now shining like tiny cosmic beacons. These knots are more than just pretty details, they are profound time capsules. Their chemical composition is a direct snapshot of the elements that were being forged in the star's outer layers in its final moments. Spectroscopic analysis reveals they are rich in helium, hydrogen, and elements like sulfur and oxygen, the building blocks that were once part of the star itself. They are not products of the nebula's later activity, they are relics of the initial explosion, making them among the oldest structures we can observe within the crab. By studying them, we are effectively conducting an archaeological dig on a stellar corpse, uncovering the layers of a star that died 1,000 years ago. Their continued existence is in itself a major puzzle. The environment inside the Crab Nebula is incredibly hostile. They are constantly bombarded by the pulsar's intense radiation, which should be boiling them away. They are also buffeted by the pulsar wind and plowing through the surrounding gas at tremendous speeds, forces that should shred them into nothing. According to simple models, these delicate structures should have been vaporized and dispersed centuries ago. The fact that they not only persist but also maintain their compact, defined shapes means they must possess some hidden source of resilience. Their secret likely lies in a combination of density and magnetic fields. It's believed these knots are incredibly dense compared to the wispy material around them. This high density gives them a kind of gravitational inertia, making them harder to tear apart. But perhaps the more important factor is that they might be magnetically confined. It's possible that the original star's magnetic field became frozen into these clumps of gas during the explosion. This intrinsic magnetic field could act like a strong container, holding the gaseous material together against the external forces trying to destroy it. It's the difference between a bag of loose feathers being blown away in a strong wind and those same feathers being tightly packed into a solid ball. The knots are the stellar equivalent of that tightly packed, resilient ball. Watching these knots move provides another layer to the story. They are not static, they are flying outward from the center of the explosion, each on its own trajectory. By tracking their motion over years, astronomers can trace their paths backward to confirm the date and location of the supernova, much like with the larger filaments. However, some knots show peculiar, non-radial motions, zipping along at angles that deviate from the general expansion. This suggests they are interacting with the complex magnetic web of the nebula, or perhaps with each other, offering clues about the invisible forces that fill the space between the visible structures. Ultimately, the survival of these knots gives us a unique benchmark for understanding the true ferocity of the nebula's interior. Their gradual erosion as matter is slowly stripped away by radiation acts as a natural clock. By measuring how quickly they are dissolving, we can better gauge the immense power of the pulsar wind and radiation field that surrounds them. These tiny, glowing fragments are more than just remnants. They are hardy survivors, enduring witnesses to a cataclysm that began a millennium ago, and their slow fade into the nebula's glow tells the final chapter of their story. This organized dance of light offers us a direct window into one of the nebula's most invisible yet powerful components, its magnetic field. The degree and angle of polarization at any given point act like a cosmic compass, tracing the orientation and even hinting at the strength of the magnetic fields that guide those spiraling electrons. By meticulously measuring the polarization across the entire nebula, astronomers can create detailed maps of this magnetic architecture. It's akin to taking a handful of iron filings and sprinkling them around a magnet, watching them line up to reveal the field's shape, except in this case, the magnetic field is vast, complex, and woven through an entire nebula, and the iron filings are measurements of light collected by the world's most powerful telescopes. What these polarization maps reveal is astonishingly intricate and deeply strange. They show a magnetic field that is far from the simple, orderly dipole pattern we might expect from a lone, spinning pulsar. Instead, the field is a tangled web of chaos and order existing side by side. Near the pulsar itself, the field lines are relatively well organized, swept into a torus or donut-like shape, aligned with the pulsar's spin equator, with powerful jets erupting from its poles. This is the pulsar's direct imprint, but as you move outward, this order breaks down dramatically. The field becomes a turbulent mess of loops, knots, and seemingly random directions, especially within the vibrant filamentary structure of the nebula's outer layers. This bizarre inconsistency is the heart of the polarization mystery. Why is the magnetic field so strong and structured in some regions, yet so weak and chaotic in others? Our standard models suggest the pulsar's wind should inflate a large, relatively uniform bubble of magnetic energy with an orderly structure that weakens gradually with distance. The Crab Nebula defiantly refuses to conform to this neat prediction. The observed patches of intense polarization right next to zones of magnetic pandemonium suggest there are local physical processes at work that our theories haven't fully accounted for. Perhaps the constant sloshing and interaction between the fast-moving pulsar wind and the slower supernova ejecta are generating powerful turbulences that constantly twist, stretch, and reorganize the magnetic field in real time. Or maybe the field itself is so strong in certain filaments that it dominates the local physics, creating isolated islands of magnetic order within the broader storm. Understanding this isn't just an academic exercise, it gets to the very core of how energy is transported and dissipated throughout the nebula. Magnetic fields act as the skeleton for the entire structure, controlling how the pulsar's wind distributes its energy, how particles are accelerated to such incredible speeds, and even how the beautiful filaments themselves are shaped and illuminated. A flawed understanding of the magnetic field means a flawed understanding of the Crab Nebula's entire engine. Every new and more detailed polarization map forces astrophysicists to go back to their simulations, to incorporate new levels of complexity and instability, inching us closer to a true comprehension of how magnetism shapes the universe's most violent and beautiful events. Just when we think we have a handle on the Crab Pulsar's clockwork reliability, it throws us another curveball, and this one is a paradox of silence. For all its predictable pulsing, the pulsar occasionally and abruptly stops. Its radio waves, which normally blast toward us with metronomic precision, will suddenly vanish for a period ranging from a few pulses to several minutes. These events are known as nulling, and they create a jarring radio silence where we expect a steady, rhythmic beat. It's as if a drummer in the world's most precise band suddenly, and without warning, drops their sticks mid-song. The mystery only deepens when we look at other parts of the electromagnetic spectrum during these radio blackouts. While the radio waves go quiet, the pulsar doesn't just power down. Incredibly, observations often show that its emissions in X-rays and gamma rays don't just continue, they can actually intensify. So, during a nulling event, the radio lighthouse beam seems to shut off, but the high-energy powerhouse at its core becomes, paradoxically, even more ferocious. This isn't a simple engine failure, it's a fundamental reconfiguration of how the pulsar is emitting its energy, a shift in the flow of power from one set of processes to another. So what could possibly cause such a bizarre and specific interruption? The leading theories all point to dramatic changes happening within the pulsar's magnetosphere, that intense, roiling region of magnetic fields and plasma surrounding the neutron star. One compelling idea is a phenomenon called magnetic field line reconnection. The pulsar's magnetic field is unimaginably complex and under immense stress. If these field lines suddenly snap and rearrange themselves into a new, more stable configuration, it could temporarily disrupt the very region where radio waves are generated. Think of it like a short circuit in a cosmic power grid, rerouting the energy away from the radio transmitters and into other, more high-voltage circuits. Another possibility involves a sudden inundation of plasma. The pulsar's surface is constantly boiling with intense heat and pressure, occasionally ejecting dense clouds of charged particles. If one of these plasma clouds were to flood the magnetosphere, it could effectively smother the radio emission process. The radio waves, which are generated by a very specific mechanism involving spiraling electrons along magnetic field lines, get absorbed or scattered by this sudden overpopulation of particles, while the processes that create X-rays and gamma rays, which occur much closer to the star's surface or in different parts of the magnetosphere, are left unaffected or even enhanced by the influx of material. These nulling events, while frustrating for astronomers who use the pulsar as a celestial timekeeper, are actually invaluable clues. They provide a rare glimpse into the otherwise invisible dynamics of the pulsar's engine room. By studying the exact timing and duration of these dropouts, and by meticulously comparing what happens across all wavelengths when they occur, scientists can start to map the different emission zones within the magnetosphere. It's like hearing a complex machine run perfectly and then learning even more about it the one time it coughs or sputters. That momentary glitch reveals which parts are connected and how the energy flows from one component to another. Each radio silence is a precious data point, helping us piece together the inner workings of one of the most extreme objects in the universe. And while the pulsar's magnetosphere can experience moments of sudden radio silence, its most dramatic and constant outward expression is a structure of breathtaking power and precision. A narrow, high-speed jet of particles that screams away from the neutron star aligned perfectly with its spin axis. This isn't a diffuse cloud or a messy outflow. It's a focused beam, a cosmic blowtorch that extends light years out into the nebula, visible as a faint but distinct tendril in X-ray and radio observations. In the chaotic storm of the Crab's heart, this jet is a startlingly straight line, a testament to an incredible focusing of energy that defies the surrounding pandemonium. The very existence of such a well-collimated jet is a major theoretical challenge. How does a turbulent, super-energetic environment like the one surrounding the Crab Pulsar produce something so narrow and stable? Our best models suggest it's born from the intense magnetic field that is tightly wound around the pulsar's spin axis. Charged particles, accelerated to near light speeds, are funneled along these open magnetic field lines that erupt from the magnetic poles. It's like water being forced through a nozzle. The immense magnetic pressure squeezes the chaotic flow of the pulsar wind into a tight, incredibly fast beam. However, maintaining that focus as the jet plows through the resisting material of the nebula is a problem that current physics struggles to fully explain. It should disperse and destabilize far more quickly than it actually does. This jet is far from a passive structure. It's an active and violent sculptor of its environment. As it rams into the slower-moving gas of the inner nebula, it creates powerful shock fronts, standing walls of energy that heat the surrounding gas to millions of degrees, causing it to glow brilliantly in X-rays. These interactions create visible knots and ripples along the jet's path, markers of its relentless push against the nebula's resistance. By studying the shape and behavior of these shocks, astronomers can effectively measure the power and pressure of the jet itself, using the nebula as a calibration tool. The Crab's jet offers a unique, up-close laboratory for understanding astrophysical jets in general, which are among the most powerful and common phenomena in the universe. We see similar, though immensely larger, jets launching from the supermassive black holes at the centers of active galaxies and from stellar mass black holes and neutron stars in binary systems. The physics of acceleration and collimation is thought to be similar across these vast scales, governed by the interplay of rotation, accretion, and magnetic fields. The Crab's jet is our closest and most detailed example of this universal engine at work, providing a crucial benchmark for testing the theories we use to explain jets that can be millions of light years long. Its relative proximity allows us to observe the fine details of its structure and interaction in a way that's impossible for more distant objects, making it an indispensable key to unlocking one of the universe's most energetic and enduring mysteries. But if we want to understand the true story of the star's death, we have to look beyond its structure and motion and into its very chemistry. Spectroscopic studies, which break down the nebula's light into a rainbow of elemental fingerprints, reveal a series of chemical anomalies that have left scientists scratching their heads. The abundances of certain elements, particularly helium and argon, are significantly different from what our established models of supernova nucleosynthesis predict. It's as if a master chef followed a famous recipe exactly, but the final dish turned out with a completely unexpected and inexplicable flavor profile. These elements are the direct products of the nuclear fusion that powered the star during its life and the intense burning that occurred in its final moments. Our models for a star of this size are quite detailed. We have a good idea of how the different layers of onion skin burning should have produced and layered specific elements, from hydrogen and helium in the outer layers to iron in the core. When that star goes supernova, the tremendous shock waves and heat are supposed to blast these layers out into space in a somewhat predictable mix. The Crab Nebula, however, stubbornly refuses to follow the script. The observed overabundance of helium and argon suggests that the layers of the star did not simply eject outward in a neat, orderly fashion. Instead, a profound and violent mixing must have occurred during the explosion itself. Imagine the innermost core of the star, where elements like argon are forged under extreme pressure and temperature, suddenly being churned upward and outward by convection currents powerful enough to shred the star apart. Meanwhile, outer layers rich in helium might have been dragged down inward before being hurled back out. This isn't a clean eruption, it's a chaotic blender, mixing the star's ingredients in ways that our current simulations are still struggling to replicate. The anomalies are a direct chemical record of that turbulence, a frozen-in snapshot of the maelstrom that was the star's final second. Another fascinating possibility is that the progenitor star itself was a chemical oddball before it ever exploded. Perhaps it had a peculiar composition from birth, having formed in a region of space already enriched by previous generations of unusual supernova. Or maybe it lost a significant portion of its outer hydrogen envelope to a binary companion star long before its death, altering the chemical balance that would later be revealed in the supernova debris. The elemental fingerprints we see today are therefore not just a record of its death, but a clue to its entire life history. Unraveling this chemical mystery is about far more than just understanding one particular nebula. These supernova products are the very stuff of life. The carbon in our cells, the oxygen we breathe, the iron in our blood, all of it was forged in the hearts of stars and scattered across the galaxy by explosions just like this one. If our models for how this mixing and enrichment works are flawed in the Crab Nebula, they might be incomplete for supernova in general. By deciphering these chemical anomalies, we are ultimately reading the instruction manual for how a galaxy seeds itself with the raw materials for new stars, planets, and potentially life itself. The Crab's strange chemistry is a message in a bottle, and we are only just beginning to understand its language. Woven throughout the entire expanse of the Crab Nebula, creating its most iconic and beautiful portrait, is a breathtakingly complex web of glowing filaments. These delicate, thread-like structures shine in vivid hues of red, blue, and green, a celestial tapestry that makes the crab one of the most photographed objects in the sky. But their serene beauty is a magnificent illusion. These are not gentle clouds of dust, they are the ghostly, glowing remains of the star's own atmosphere, violently torn apart and cast into space during the supernova explosion almost 1,000 years ago. They are the visible skeleton of the cataclysm, and their continued illumination is one of the nebula's most dynamic and strange processes. The reason these filaments glow so brightly gets to the very heart of the crab's enduring energy. They are not shining with their own light like a star. Instead, they are being fluorescently lit by an immense and powerful external source, the relentless radiation from the central pulsar. The gases that make up these filaments, primarily hydrogen, helium, oxygen, and sulfur, are constantly bombarded by the pulsar's intense ultraviolet light and X-rays. This high-energy radiation is so fierce that it strips electrons away from their atoms, a process we call ionization. Later, when these free electrons are recaptured by the atoms, they release that stored energy, but at a much lower energy level as visible light. Each element has its own specific color fingerprint. Oxygen glows a characteristic greenish blue, while hydrogen and nitrogen produce rich reds. The nebula is in effect a vast cosmic neon sign, with the Crab Pulsar acting as the powerful transformer that keeps it permanently switched on. What makes these structures so bizarre and fascinating to astronomers isn't just that they glow, but how they glow and why they maintain such incredibly sharp, crisp boundaries. In most gas clouds in space, material tends to diffuse and spread out, creating soft, blurry edges. The crab's filaments, by contrast, are remarkably thin and well-defined, like veins of lightning frozen in place. This razor-sharp definition is a clear sign that something is actively confining them, preventing them from simply dissipating into the void. That something is believed to be the nebula's own magnetic field, which is frozen into the ionized gas. This magnetic pressure acts like an invisible container, sculpting the expanding gas into these long, thin, rope-like structures and holding them together against the forces of turbulence and expansion. Furthermore, this isn't a static display. The illumination is a constant and rapidly changing phenomenon, because the pulsar's power output can fluctuate with its gusty wind and the occasional gamma-ray flare. The intensity of the light hitting the filaments changes in response. A surge of energy from the center can make entire sections of the filamentary network suddenly brighten, as a wave of new ionization washes through them. Time-lapse observations reveal that the nebula is subtly pulsing and flickering in tandem with the rhythm of its central engine, a light echo playing out across a volume of space trillions of miles wide. This makes the filaments a real-time energy map, a visible gauge showing us how the pulsar's power is distributed and absorbed throughout its domain. By studying the light from these filaments through a spectrometer, astronomers can read this story in incredible detail. They can determine the exact temperature, density, and chemical composition of the gas. They can measure the velocities of different filaments as they rush away from the center or interact with each other. This data reveals that the environment within the filaments is incredibly hostile. The gas is roaring outward at thousands of kilometers per second and is so turbulent that it would tear apart any solid object in an instant. The fact that these delicate-looking structures not only survive but thrive in this maelstrom is a testament to the incredible confining power of magnetic fields and the unending stream of energy from the stellar corpse at their heart. They are both a relic of a past explosion and a living, breathing testament to the powerful forces that continue to shape its aftermath. While the inner nebula shines with visible light from its glowing filaments, the crab also broadcasts a message in the most energetic language the universe can speak, a constant, intense whisper of very high-energy gamma rays. These are not the gamma-ray flares that erupt without warning. This is a steady, seething hum of power, making the Crab Nebula one of the brightest and most persistent beacons in the TV sky, the Terra electronvolt regime, where each photon carries trillions of times more energy than visible light. Detecting this signal is like trying to hear a single, specific instrument in a cosmic symphony played at the volume of a supernova. and it challenges our very understanding of how nature can accelerate particles to such extreme velocities. To even observe this faint, high-energy whisper, we require a completely different kind of telescope. Gamma rays of this energy cannot be focused by lenses or mirrors. They are so powerful that when they strike Earth's atmosphere, they don't simply pass through. Instead, they explode. Each TV gamma ray photon triggers a cascading shower of secondary particles that streaks toward the ground at near light speed, emitting a faint, incredibly brief flash of bluish Cherenkov radiation in the air. Ground-based observatories like Veritas in Arizona and HESS in Namibia are designed to detect these fleeting flashes. Their arrays of large, ultra-sensitive mirrors act like giant light buckets, collecting this faint glow and using it to reconstruct the energy and direction of the original gamma ray that started the cascade millions of feet above. The mere existence of this steady TV glow is not the surprise. Our models predicted the crab would be a source. The profound mystery lies in its intensity and its specific distribution across the nebula. According to our standard theories of diffusive shock acceleration, the process we believe powers most cosmic particle accelerators, there should be a natural limit to how much energy an electron can gain from the nebula's shocks and magnetic fields. Yet, the observed TV emission is far brighter than this theoretical limit should allow. The electrons responsible must be reaching energies that, by all rights, should be impossible within the confines of the nebula, pushing them into a regime where our comfortable physics textbooks start to need new chapters. Furthermore, this powerful emission doesn't come from where we might most expect it. While one might assume the highest energy processes happen closest to the pulsar, detailed maps from these observatories reveal that the most intense TV gamma rays are not originating from the central engine itself. Instead, they appear to be generated further out, in the vicinity of the nebula's intricate filamentary structure, and particularly near the outer edges of the torus of material surrounding the pulsar. This forces a radical rethinking of the acceleration mechanism. It suggests that the entire nebula, not just the inner shocks, is acting as a gigantic and highly efficient accelerator, with particles gaining immense boosts of energy as they travel through and interact with the complex web of magnetic fields and turbulent plasma. The leading explanation for how this happens is a two-step process called inverse Compton scattering. First, the ultra-relativistic electrons, already accelerated to near light speed by the pulsar wind nebula, need a target to collide with. They find it in the form of lower-energy photons that fill the nebula, including the visible light from the glowing filaments and even the pervasive relic radiation from the Big Bang itself, the cosmic microwave background. In a tremendous transfer of energy, the high-speed electron slams into this low-energy photon and, in effect, donates a huge amount of its own kinetic energy to it, boosting that meek photon up into the monstrously high-energy TV gamma ray regime. It's the cosmic equivalent of a speeding bullet striking a stationary ping-pong ball and launching it with the force of a cannonball. The ongoing debate among astrophysicists is not about if this happens, but where and how it becomes so incredibly efficient. Some models propose that the acceleration is happening continuously throughout the nebula as electrons diffuse outward, gaining little bits of energy from multiple turbulent encounters. Others suggest that specific, localized regions like the standing shock waves at the base of the jet or at the interface between the pulsar wind and the supernova ejector are the primary factories for these ultra-high-energy particles. Each new observation from the current generation of telescopes and the upcoming more sensitive Cherenkov telescope array brings more detail to these maps, allowing scientists to pinpoint the exact locations of the most powerful acceleration sites. This isn't just an arcane debate about one nebula. By cracking the code of the Crab's TV engine, we are developing the fundamental physics needed to understand the most violent and energetic particle accelerators throughout the cosmos, from distant active galaxies to the remnants of other supernovae. This entire breathtaking spectacle, from the shimmering filaments to the violent gamma-ray flares, is fundamentally powered by a single, overarching structure, the Pulsar Wind Nebula. Think of it as a vast, dynamic bubble that the Crab Pulsar has blown around itself, a cocoon of pure energy inflated by its own relentless power. This isn't a simple, static balloon. It's a churning, turbulent, and incredibly complex system where the hyper-energetic wind from the central neutron star slams into, pushes against, and gradually expands into the slower-moving debris from the ancient supernova explosion. It's a cosmic battle zone, a place where two different epochs of the star's death are colliding, and the physics governing this interaction are far more intricate and surprising than we ever anticipated. The heart of this system is, of course, the pulsar wind itself, that supersonic torrent of radiation and charged particles that races outward from the neutron star. But as this wind travels, it doesn't just smoothly dissipate. It eventually encounters a formidable obstacle, the shell of much denser, much slower material that was ejected during the supernova itself. The boundary where these two immense forces meet is known as the termination shock, and it's one of the most critical and bizarre regions in the entire nebula. This is where the orderly, focused wind from the pulsar is suddenly and violently decelerated, transferring its colossal energy into the surrounding environment and creating the chaotic structures we observe, like the rippling wisps and the shifting X-ray rings. Computer simulations that try to model this entire ecosystem consistently run into a wall of complexity. The models, which rely on the laws of magnetohydrodynamics, the study of how magnetic fields and electrically conductive fluids like plasma interact, predict a certain amount of turbulence. But the actual observations from telescopes like Chandra and Hubble show a level of intricate structure and rampant instability that the simulations struggle to replicate. It seems there are processes at work within this plasma that we haven't yet fully coded into our equations. The nebula is filled with fiendishly complex phenomena like Rayleigh-Taylor instabilities, where lighter fluid pushes against a heavier one, creating the beautiful finger-like filaments, and Kelvin-Helmholtz instabilities, which occur when two fluids slide past one another at different speeds, creating swirling vortexes and waves along their boundary. A Crab is essentially demonstrating advanced plasma physics in action, on a scale we could never hope to recreate in a lab on Earth. One of the most significant surprises is how this energetic bubble is not just expanding but also cooling. The prevailing theory suggested that the Pulsar Wind Nebula would expand adiabatically, meaning it would cool simply because it's growing into a larger volume, like gas escaping from a pressurized can. While this does happen, observations reveal that the nebula is cooling far more efficiently than that simple model allows. This points to additional, potent cooling mechanisms at work. The leading candidate is radiation cooling. The incredibly energetic electrons within the nebula are losing a substantial amount of their energy not through expansion, but by emitting it away as light across the spectrum from radio waves to X-rays. This radiant energy loss acts like a constant bleed on the system's power, siphoning off energy and allowing the plasma to cool more rapidly than expected. Furthermore, the entire Wind Nebula is not a uniform entity. It's a structured hierarchy of energy. The highest energy processes, those producing X-rays and gamma rays, are concentrated in the inner regions, close to the pulsar and its termination shock. As you move outward through the nebula, the particles lose energy and radiate at progressively longer, less energetic wavelengths. This creates a kind of energy gradient, with the inner heart of the nebula glowing in X-rays, surrounded by a larger shell visible in optical light from the filaments, and an even larger, fainter halo detectable in radio waves. This structure tells the story of the energy's journey, from its explosive birth at the pulsar to its eventual dissipation into the wider interstellar medium. By studying the Crab Nebula, we are not just looking at a beautiful cloud. we are using it as the universe's premier laboratory to understand the life cycle of energy and matter in the most extreme environments imaginable. This celestial spectacle, witnessed by human eyes nearly 1,000 years ago, offers a profound connection between ancient astronomy and modern science. On a July morning in the year 1054, as recorded by Chinese court astronomers of the Song dynasty, a new star suddenly appeared in the constellation of Taurus, shining so brilliantly that it was visible in broad daylight for 23 consecutive days. They called it a guest star, noting its eerie reddish-white color and its position near the star we now know as Zeta Tauri. For well over 600 days, this celestial visitor remained visible to the naked eye before finally fading from view, leaving behind a mystery that would captivate astronomers for centuries. These meticulous Chinese records weren't alone. Across the world, other cultures were documenting the same extraordinary event. Arab astronomers, including the Persian scholar Ibn Batlan, noted the brilliant star in their medical texts, interpreting it through their astrological traditions. Japanese stargazers recorded it in their court documents, calling it a bakuro, or mysterious star. Perhaps most intriguingly, there's compelling evidence that Native American cultures witnessed and recorded the event as well. A petroglyph found in Choco Canyon, New Mexico, shows a hand, a crescent moon, and a large star in a configuration that matches exactly with the position of the moon relative to the supernova on the morning of July 5, 1054, the day the event would have been at its most spectacular dawn appearance. What makes these historical accounts so valuable to modern science isn't just their poetic descriptions, but their precise observational data. The duration of visibility, particularly those 23 days of daylight visibility, provides crucial information about the supernova's peak brightness. Astronomers calculate that to be visible during the day, the supernova must have reached an apparent magnitude of around -6 or 7, making it roughly 4 times brighter than Venus at its brightest and only slightly dimmer than a full moon. This exceptional brightness, combined with the long duration of its visibility, tells us that the Crab Nebula's progenitor star wasn't just any supernova, it was an exceptionally energetic event. This historical data helps solve one puzzle while creating another. The extreme brightness aligns with what we now know about Type II supernova, the explosive death of a massive star, but the long duration suggests something unusual about the environment around the exploding star. Modern simulations indicate that the supernova's light curve, its pattern of brightening and fading, was likely enhanced by the star's interaction with material it had ejected before its final collapse. Essentially, the shock wave from the explosion would have plowed through this pre-existing circumstellar material, heating it to incredible temperatures and causing it to glow brightly for an extended period, like adding extra fuel to a fire. This would explain both the initial brilliance and the remarkably long fading period documented by ancient astronomers. The historical records also provide a vital anchor point for measuring the nebula's expansion. When astronomers traced back the motion of the modern filaments, calculating their velocities backward through time, they all converged to a single point around the year 1054 with an uncertainty of only a few decades. This incredible agreement between ancient human observation and modern astrophysical measurement creates one of the most satisfying validations in all of astronomy, a direct link between the careful sky watching of our ancestors and our current understanding of stellar evolution. Yet the historical accounts also raise cultural questions about why the event wasn't more widely documented, particularly in European records. While some researchers have suggested possible references in Irish monasteries or Byzantine texts, the lack of clear European documentation remains puzzling. Some historians speculate that prevailing religious doctrines in medieval Europe might have discouraged the recording of such celestial anomalies, viewing them as atmospheric phenomena rather than astronomical events, or perhaps even as ill omens best left unrecorded. This cultural filter reminds us that the history of astronomy isn't just about what was observed, but about who was watching and how they chose to interpret the mysteries unfolding above them. For every action, there is an equal and opposite reaction, or so the fundamental laws of physics would lead us to believe. This principle of symmetry appears to be written into the very fabric of the universe, and in astrophysics, it often manifests in the form of bipolar jets. When we see a powerful jet erupting from a celestial object, whether it's a supermassive black hole or a young stellar object, we almost invariably expect to find a second counterjet shooting out in the exact opposite direction. It's a balanced, symmetrical system, a cosmic seesaw. This is why the case of the Crab Pulsar's potential counterjet is so deeply puzzling. While its primary jet is a brilliant and well-studied feature, its theoretical twin is notoriously, almost frustratingly, elusive. The primary jet, blazing with X-rays and radio waves, is a textbook example of focused power. It's a clear, narrow beam aligned with the pulsar's spin axis, demonstrating the incredible ordering influence of its magnetic field. Given this, our models strongly predict that an identical jet should be emanating from the opposite pole. The physics of the pulsar's magnetosphere, the way its magnetic field funnels particles outward from both magnetic poles, seems to demand it. We've detected these counterjets in other, similar systems, which makes the Crab's missing counterpart a glaring exception to the rule. The question isn't just about finding a faint structure, it's about why the fundamental symmetry we expect appears to be broken. So, where is it? Astronomers have combed through data from the Chandra X-ray Observatory and powerful radio telescopes, searching for any faint hint of this ghostly partner. The evidence thus far is tentative and controversial. Some analyses of deep X-ray images suggest a faint, diffuse glow extending in the opposite direction from the main jet, a wisp of emission that could be the counterjet's faded signature. Others argue this faint emission is merely a trick of the light, a background fluctuation or an unrelated part of the nebula's general turbulent glow. The signal is so weak and ambiguous that the scientific community remains divided. Its very existence is still a topic of active debate. If the counterjet is truly absent or drastically weaker, it forces a radical rethinking of the environment around the neutron star. One compelling theory points to the intense, lopsided drag of the surrounding nebula. The Crab Nebula is not a uniform, hollow sphere. It's filled with a chaotic and uneven distribution of gas, dust, and magnetic fields. It's possible that the material on one side of the pulsar is significantly denser than on the other. A nascent counterjet trying to form and push outward could be immediately smothered by this thicker, more resistant environment, its energy dissipated and absorbed before it can ever properly form into a coherent beam. The main jet, by contrast, might have the fortune of pointing into a clearer, less obstructive path, allowing it to race away unimpeded for light years. Another fascinating possibility involves the birth of the neutron star itself. When the core of the progenitor star collapsed, the newborn pulsar likely received a tremendous kick from asymmetrically emitted neutrinos or gravitational waves, sending it recoiling through the supernova debris at hundreds of miles per second. This kick would not have been perfectly aligned with the original rotation axis. This means the pulsar's current direction of motion, its velocity vector, and its spin axis are probably misaligned. As the pulsar plows through the nebula, it creates a bow shock in front of it, much like the wave at the front of a speedboat. This bow shock is an asymmetric structure, and it could be crushing the counterjet on one side while leaving the main jet on the other side relatively untouched. The geometry of the pulsar's movement through its own nebula might be actively stifling one of its own jets. The implications of this missing jet extend far beyond the Crab. If its absence is confirmed and explained, it would provide a crucial lesson about how the local environment can dramatically alter the intrinsic properties of a central engine. It would show that the beautiful symmetry we often attribute to these systems can be an illusion. easily broken by the messy, real-world conditions of their surroundings. For astronomers studying jets from distant quasars or microquasars, the crab serves as a critical reminder that what we see is not just the engine itself, but a complex interaction between that engine and its cosmic habitat. The search for the crab's counter-jet is more than a hunt for a faint structure. It is a test of our deepest assumptions about symmetry and power in the violent universe. But the Crab Pulsar's surprises aren't limited to its high-energy outbursts or its moments of radio silence. Sometimes its most stunning displays are ones we could, in theory, see with our own eyes. Amidst its steady, clockwork pulses across the electromagnetic spectrum, the neutron star occasionally unleashes something extraordinary, incredibly brief, fantastically intense flashes of visible light. These are not the faint, regular pulses we could barely detect with a powerful telescope. These are colossal, runaway bursts of optical energy that can make the pulsar hundreds of times brighter than normal for a mere fraction of a millisecond. They are the cosmic equivalent of a lightning strike from a clear sky, a sudden and brilliant defiance of the star's usual metronomic rhythm. Capturing these fleeting events requires a special kind of astronomical observation known as high-speed photometry. Imagine trying to photograph a hummingbird's wings in sharp detail with a standard camera. You'd just get a blur. To freeze the action, you need an extremely fast shutter speed. Astronomers use this same principle, employing specially designed instruments on large telescopes that can take thousands of measurements of a star's brightness every single second. It's through this rapid-fire stargazing that we've been able to catch the Crab Pulsar in the act, documenting these spectacular optical flashes that come and go in the blink of an eye. What makes these flashes so mysterious is their tight correlation with the pulsar's other activities. They don't happen at random, they are almost always perfectly synchronized with the pulsar's radio pulses. In fact, the brightest optical flashes coincide precisely with the pulsar's so-called giant radio pulses, moments when its regular radio beacon suddenly intensifies by a factor of hundreds or even thousands. This powerful link tells us that the mechanism behind both phenomena is deeply connected, originating from the same violent process within the pulsar's magnetosphere. However, the optical light isn't just a simple brightening. It represents a massive, disproportionate surge of energy in the visible part of the spectrum, suggesting that something extraordinary is happening during these specific rotations. The leading theory points back to that familiar suspect, magnetic reconnection. The pulsar's magnetosphere is a roiling sea of unimaginably powerful and twisted magnetic field lines under incredible stress. We think that during a giant pulse event, a sudden and catastrophic reconfiguration of these field lines occurs. They snap and reconnect into a new, more stable arrangement, releasing a tremendous amount of pent-up magnetic energy all at once in a specific, concentrated region. This immense release doesn't just accelerate particles to produce a giant radio pulse. It also superheats the local plasma to fantastic temperatures, causing it to briefly blaze with intense visible light. It's a microscopic stellar explosion happening just above the surface of the neutron star. Another fascinating idea suggests these flashes could be a form of coherent emission, a process similar to how a laser works. Normally, light from a celestial object is incoherent. Each photon is emitted randomly and independently. But under certain extreme conditions, particles can be made to act in unison, emitting light waves that are all in sync. This coordinated emission creates an incredibly powerful, focused beam of light. It's possible that within the chaotic environment of a giant pulse, the conditions momentarily become just right for this coherent process to take place at optical wavelengths, resulting in a brilliant flash that far exceeds the pulsar's normal output. Studying these optical flashes provides a uniquely valuable window into the pulsar's engine room. While radio waves and X-rays are generated by processes that occur throughout a larger volume of the magnetosphere, these intense optical flashes likely originate from a very specific and incredibly small region, perhaps only a few hundred meters across. By meticulously timing these flashes and comparing them to the accompanying radio waves, astronomers can perform a form of cosmic triangulation, pinpointing the exact location where this explosive energy release is happening. Each flash is like a lightning strike that momentarily illuminates the inner workings of the machine, giving us a split-second glimpse into the complex physics governing one of the most extreme environments in the universe. If you could tune a radio to the frequency of the Crab Nebula, you would hear more than just the steady beat of its central pulsar. You would detect a vast, shimmering shell of radio waves enveloping the entire structure. This radio emission paints a picture of the nebula that is both familiar and strangely different from its visible light portrait. It outlines the same general form, but with one crucial and puzzling distinction. It possesses an incredibly sharp outer boundary. Unlike the wispy, filamentary edges we see in optical images, the radio map of the crab ends abruptly, as if the entire nebula is encased within a thin, invisible skin. This sudden cutoff, where the radio emission plummets to near nothingness, is one of the most consistent yet least understood features of this cosmic object. This phenomenon, often called the skin effect, isn't a simple visual artifact. It's a real physical boundary that tells a story about the life cycle of electrons and the power of magnetic fields. The radio waves themselves are generated by a process called synchrotron radiation, the same mechanism that creates the nebula's X-rays and visible light, but from much lower energy electrons. These electrons, spiraling around magnetic field lines at nearly the speed of light, emit their energy as radio waves. The sharp edge suggests that something is preventing these electrons from diffusing outward past a certain point, effectively trapping them inside a defined bubble and creating a radio-bright interior that contrasts sharply with the dark space beyond its border. Unraveling the mystery of this skin requires the unique capabilities of radio telescopes, particularly vast arrays like the Carl G. Jansky Very Large Array or VLAR in New Mexico. The VLA doesn't take pictures in the traditional sense. Its 27-dish antennas work together as a single, colossal eye, measuring the faint radio whispers from space. By combining the signals from all these antennas and using a technique called interferometry, astronomers can create exquisitely detailed maps of the radio sky, resolving fine structure within nebulae and, crucially, defining their edges with phenomenal precision. It is through years of such observations that the razor-sharp profile of the crab's radio shell has been so clearly defined. But what creates this containing barrier? Astronomers are investigating two compelling and possibly interconnected explanations. The first involves a process known as synchrotron cooling. The electrons that produce radio waves are the oldest and least energetic within the nebula. They've been radiating away their energy for centuries since the supernova. As they lose energy, their ability to penetrate outward through the nebula's own magnetic field diminishes. Think of it like a group of runners. The most energetic sprint far ahead, while the exhausted ones eventually slow to a walk and fall behind. The radio-emitting electrons are the exhausted ones, and the sharp edge may simply mark the farthest point their dwindling energy allows them to reach before they can no longer effectively produce detectable radio waves. The second, and perhaps more dominant, theory points to an external force, the pressure of the interstellar medium. The Crab Nebula is not expanding into a perfect vacuum. It's plowing into a very thin but non-zero soup of gas and dust that fills the space between stars. This material, while diffuse, exerts a constant, gentle pressure on the nebula's expanding shell. The radio-emitting electrons and their associated magnetic fields are contained within this shell. As the expansion continues, this external pressure acts like a flexible but strong membrane, preventing the lowest energy electrons from leaking out and effectively sculpting that observed sharp boundary. The skin, in this case, is the point where the outward pressure from the pulsar wind nebula finally balances against the inward pressure of the galactic environment. The true puzzle lies in the skin's remarkable uniformity and persistence. A simple pressure balance might create a generally rounded shape, but it wouldn't necessarily explain the consistent sharpness of the drop-off across the entire nebula's surface. This suggests a more complex and global process is at work, likely involving the nebula's magnetic field. The field itself may be amplified and compressed at the very outer edge, creating a magnetic wall that effectively reflects the radio-emitting electrons back inward, ensuring they remain confined and contribute to the bright interior emission. This magnetic barrier would serve as the ultimate containing layer, the true skin that gives the Crab Nebula its distinct radio silhouette. Studying this edge is therefore about more than just mapping a boundary. It's a direct way to measure the invisible forces of pressure and magnetism that govern the nebula's interaction with the wider galaxy. Despite the intense and orderly radiation pouring from the pulsar, the very dust it heats behaves in a deeply unpredictable way, creating a thermal puzzle known as the dust temperature paradox. Common sense would suggest a simple, elegant gradient. The closer a dust grain is to the central powerhouse, the hotter it should be, glowing more intensely in infrared light as it absorbs that fierce energy. Yet, when astronomers map the crab's infrared glow, that neat correlation shatters. They find blisteringly hot dust grains surprisingly far from the pulsar, while some regions much closer in remain curiously cooler than expected. This bizarre and inconsistent heating pattern tells us that the nebula's interior is far more complex than a simple oven with a single heating element. It's a chaotic kitchen where the ingredients themselves are constantly changing. Unraveling this thermal mystery requires the sharp eyes of infrared telescopes. Instruments like the Spitzer Space Telescope and, more recently, the James Webb Space Telescope are essential because they see the universe in the specific wavelength where warm dust likes to shine. By analyzing this infrared light, astronomers can do more than just map where the dust is. They can take its temperature. Each wavelength of infrared light corresponds to a specific thermal energy, allowing scientists to create detailed temperature maps of the nebula's dusty components. It's these precise maps that reveal the paradox in stunning detail, showing a mottled and patchy thermal landscape that defies easy explanation. So why would a dust grain far from the pulsar be as hot as its neighbor right next to it? The answer likely lies in the nature of the grains themselves. Not all dust is created equal. A grain's temperature depends less on its simple location and more on its efficiency at absorbing the pulsar's light, which is governed by its size, shape, and chemical composition. Imagine two rocks sitting in sunlight. A small, dark black stone will get scorching hot, while a large, light-colored boulder right beside it will stay relatively cool. In the Crab Nebula, we might be seeing a similar effect on a cosmic scale. A tiny, nanoscale carbon grain far out in the nebula could absorb energy with incredible efficiency, rocketing to extreme temperatures, while a larger, silicate-based grain closer to the pulsar might be less efficient and thus remain cooler. This introduces the fascinating possibility that we are not looking at a uniform population of dust, but a wild assortment of different materials and sizes, all forged in the supernova and then subjected to 1,000 years of brutal irradiation and shock waves. Some of these grains might have exotic compositions we haven't even identified yet, compounds that form only in such extreme environments and interact with light in entirely novel ways. Alternatively, the intense radiation might be actively processing the dust, shattering larger grains into tiny, superheatable fragments, or perhaps even assembling new, unusual molecules on their surfaces that change their thermal properties. The dust itself is not a passive passenger, it's an active participant in the nebula's physics. The implications of solving this paradox stretch far beyond the boundaries of the Crab Nebula. Dust is more than just cosmic decoration. It is the fundamental building block for future planets and life. Supernova are the primary foundries that manufacture and disperse these heavy elements throughout the galaxy. If the dust in a well-studied remnant like the crab has properties and behaviors we don't fully understand, then our estimates of how much dust survives these explosions and how it is distributed could be fundamentally flawed. By deciphering why some grains are hot and others are cold, we are ultimately reading the instruction manual for how a galaxy seeds itself with the raw materials for new solar systems. The crab's dust temperature paradox is therefore a critical piece of the puzzle of our own cosmic origins, a reminder that even the smallest particles can hold the biggest secrets. Yet even the strange thermal behavior of its dust is just one piece of a much larger, invisible structure that the Crab Nebula imposes upon our galaxy. Surrounding the brilliant cloud of glowing gas is a vast, diffuse halo of the most energetic particles nature can produce, cosmic rays. These are not rays of light but atomic nuclei, mostly protons, that have been accelerated to nearly the speed of light. They are invisible, silent, and constantly barrage our planet, but the crab is a known source of these enigmatic particles, creating an immense, poorly mapped corona of power that extends far beyond the nebula's visible boundaries. The central question isn't just how these particles are made, but how they break free. We know the primary accelerator, the Crab Pulsar, and its surrounding shock waves provide a perfect engine with intense magnetic fields that can whip charged particles up to tremendous energies. But the nebula itself should act as a magnetic bottle, trapping these particles within its glowing filaments for long periods. For a cosmic ray to reach us, it must somehow escape this confinement, leaking out into the wider galaxy. The process by which they diffuse through the nebula's tangled magnetic web and then propagate across interstellar space is one of the great unsolved puzzles in connecting a specific source like the crab to the cosmic rays we detect here at Earth. Detecting this halo directly is a monumental challenge. You cannot image a cosmic ray, you can only catch it when it strikes something. Large observatories like the Pierre-Auger Observatory or the Telescope Array use thousands of sensors spread across miles of desert to detect the vast showers of secondary particles created when a single high-energy cosmic ray slams into our atmosphere. When an exceptionally powerful one is detected, scientists can attempt to trace its path backward across the galaxy. While it's nearly impossible to pin one specific particle to one specific source like the crab, statistical overabundances from the nebula's general direction provide compelling indirect evidence of its contribution. A more promising indirect method involves looking for the telltale signs of the cosmic ray's journey. As these charged protons escape the nebula and travel through the galaxy, they must interact with the thin gas and ambient light of the interstellar medium. These interactions produce very high-energy gamma rays. By using gamma-ray telescopes to map the space around the Crab Nebula, astronomers are hunting for this faint, extended glow, a gamma-ray halo that would act as a ghostly map of the escaped cosmic rays spreading out from their source. Finding this halo would finally allow us to measure the size and energy distribution of this invisible corona, revealing how efficiently the crab is seeding our galactic neighborhood with these atomic bullets. Understanding this process is about far more than just one nebula. Cosmic rays play a crucial role in the ecology of the galaxy. Their energy contributes to heating the interstellar gas that will one day form new stars. They even influence the chemistry of that gas, driving reactions that can lead to the formation of complex molecules. By studying how the Crab Nebula generates and releases its cosmic rays, we are essentially learning how stellar death provides the energy and the raw materials for the next cycle of stellar birth. This invisible halo is the nebula's final and most enduring influence, a legacy of energy that will persist long after the glowing gases have faded from view. And while the nebula's outer shell expands and its magnetic fields churn, the very heart of the entire system is not sitting still. the Crab Pulsar, that city-sized powerhouse, is on the move. It is drifting through the vast cloud of its own, making at a startling speed of about 125 kilometers per second. If you could watch this motion play out over centuries, you would see the pulsar slowly but decisively carving a path through the nebula, no longer sitting at the precise center of the explosion that created it. This movement, known as its proper motion, adds a whole new layer of dynamic complexity to an already chaotic system. Tracking this subtle drift across the immense gulf of space is a feat of precision astronomy. The method relies on a simple principle: comparing the pulsar's position against a fixed background of much more distant quasars, which are so far away they appear motionless. Using very long baseline interferometry, which links radio telescopes across continents to create a virtual telescope the size of the Earth itself, astronomers can measure the pulsar's minuscule shift in the sky with astounding accuracy. These observations confirm that the neutron star is heading in a south by southeast direction, a trajectory that has profound implications for the shape of the nebula surrounding it. This motion is not a gentle glide, it's a supersonic sprint. The pulsar is moving so fast that it's outpacing the expansion of the nebula itself, plowing through the surrounding gas like a speedboat on a cosmic lake. This creates a brilliant, curved bow shock wave ahead of it, a standing wall of energy where the pulsar wind rams headlong into the relatively stagnant nebula material. Behind it, the pulsar leaves a wake of disturbed gas and tangled magnetic fields, contributing significantly to the overall asymmetry we see in the nebula's structure. The entire system is not a perfectly symmetrical bubble. It's lopsided, stretched and compressed by the movement of its central engine. The million-dollar question is, what gave it this kick? A star is not born with this kind of velocity. It is imparted during the supernova explosion itself. When the core of a massive star collapses, the process is not perfectly symmetrical. The leading theory suggests that a tremendous imbalance in the way neutrinos are emitted, or perhaps a violent sloshing of material in the instants before the collapse, can act like a rocket engine, shooting the newly formed neutron star off in one direction. It's also possible that the gravitational tug of war in a binary system, if the progenitor star had a companion, could have influenced its trajectory, though no such partner star has ever been found. The speed and direction of the Crab Pulsar's motion are crucial clues for astrophysicists trying to reverse engineer the supernova of 1054. By studying its path, they can test sophisticated computer models of core collapse explosions, helping to determine which mechanisms are capable of producing such a powerful recoil. This isn't just about understanding one dead star, it's about deciphering the fundamental physics of stellar death, a process that seeds the galaxy with the elements necessary for planets and life. The drifting pulsar is a silent witness to its own violent birth, and its path through space is the lasting signature of that ancient cataclysm. Encircling the Crab Pulsar like a fiery, cosmic bullseye is one of its most defining and brilliantly bizarre features, a dynamic ring of intense emission that marks the ultimate boundary of the star's direct influence. This torus or donut-shaped structure isn't just a static halo of light. It's the visible shock front where the pulsar's unfathomably powerful wind slams into the slower-moving debris of the surrounding nebula, an event of constant, violent energy transfer that we can actually see. In X-ray images from the Chandra Observatory, this ring glows with an unearthly blue intensity, a stark, luminous circle that provides a stunningly clear map of where the pulsar's dominion ends and the greater nebula's chaotic realm begins. The physics of this ring is a story of sudden, catastrophic deceleration. The pulsar wind is a torrent of radiation and particles moving at nearly the speed of light. But as it races outward, it eventually encounters the much denser shell of gas ejected during the supernova explosion centuries earlier. The transition is immediate and violent. It's the astrophysical equivalent of water from a fire hose hitting a brick wall. The wind particles moving at relativistic speeds are forced to break almost instantaneously, and in doing so, they convert their immense kinetic energy into radiation, causing this boundary to blaze across the electromagnetic spectrum. This standing shock wave, known as the termination shock, is the engine behind the brilliant ring we observe. What makes this structure so crucial for scientists is that it acts as a direct and powerful diagnostic tool, a natural laboratory for measuring the pulsar's output. The ring's size and shape are not arbitrary. They are determined by a precise balance of pressures. The outward pressure from the pulsar wind pushes on the ring, trying to expand it, while the inward pressure from the surrounding nebula, a combination of hot gas and magnetic fields, pushes back, confining it. By carefully measuring the ring's diameter, astronomers can effectively take the pressure of the pulsar wind. A larger ring indicates a more powerful wind is pushing harder against its confines, while a smaller, more compressed ring suggests the nebula is winning the struggle. But the ring is far from a perfect, steady circle. Its appearance is dynamic and often uneven, with sections that appear brighter, dimmer, or slightly distorted. These variations are a real-time readout of the gustiness of the pulsar wind itself. Remember, the wind isn't a smooth, constant stream. Its intensity and density fluctuate as the complex machinations of the pulsar's magnetosphere play out. A surge in the wind's power will cause a corresponding brightening in a section of the ring as more energy is dumped into the shock. A temporary lull will make it dim. By watching these changes, astronomers are essentially monitoring the heartbeat of the pulsar's engine, seeing how its power output varies from moment to moment. The ring's structure also provides an unparalleled way to measure the strength and configuration of the magnetic field at this critical boundary. The synchrotron radiation that makes the ring so bright in X-rays is produced by electrons spiraling around magnetic field lines. The specific properties of this light, its intensity, and how it's polarized tell us about the magnetic field's strength and orientation. Observations reveal that the magnetic field within the ring is not a simple loop but is incredibly tangled, a chaotic web generated by the same instabilities that make the ring ripple and change. Studying this allows us to understand how magnetic energy is generated, amplified, and ultimately dissipated in one of the most extreme environments imaginable. This luminous ring is therefore much more than a beautiful accident of physics. It is a fundamental calibration point, a cosmic gauge that allows us to quantify the incredible forces at work within the Crab Nebula. By decoding its whispers of light, we can measure the pulsar's energy loss, map its gusty wind, and probe the invisible magnetic fields that govern the entire system's behavior, bringing us closer to understanding the life cycle of power from a dead star. Moving beyond the infrared and visible light, the Crab Nebula reveals yet another layer of its energetic puzzle in the ultraviolet part of the spectrum. While the Hubble Space Telescope's stunning optical images often steal the spotlight, its keen ultraviolet vision has uncovered a pervasive and strangely intense UV glow, particularly concentrated within the intricate network of filaments. This isn't just a dim echo of the optical light. It's a significant and somewhat unexpected excess of energy that challenges our understanding of how the nebula's various components interact and share their power. This ultraviolet light primarily originates from two distinct processes. The first comes from the intense heating of the nebula's gaseous filaments. The same fierce radiation from the pulsar that ionizes gas to create the beautiful visible glow also energizes it to even higher states, causing it to emit light at these shorter, more energetic ultraviolet wavelengths. The second source is known as light scattering, where the relentless stream of UV photons from the central pulsar itself bounces off or scatters from free electrons and even dust grains within the filaments. This process effectively redirects the pulsar's innate UV output, smearing it across the nebula and making the entire structure shine in this high-energy light. The peculiar part isn't the mere presence of UV light, but its sheer intensity and distribution. When astronomers add up all the known energy sources, the pulsar's direct output, the emission from heated gas, the synchrotron radiation, the amount of ultraviolet light they observe is greater than what these models predict. This UV excess implies there are additional physical processes at work, or that our current models are underestimating the efficiency of the ones we already know about. It suggests that the transfer of energy from the pulsar to the nebula is even more complex and effective than we thought. Hubble's role in this investigation has been absolutely critical. Its Space Telescope Imaging Spectrograph, or STIS, is uniquely capable of not only mapping where this UV light is coming from, but also of breaking it down into a detailed spectrum. This spectral data acts like a chemical fingerprint, allowing scientists to identify the specific elements responsible for the emission, and more importantly, to measure their temperature and density. By comparing these UV maps with simultaneous observations in X-ray, optical, and infrared light from other observatories, astronomers can construct a complete multi-wavelength energy budget for the entire nebula, seeing how energy is absorbed, transformed, and re-radiated across the entire electromagnetic spectrum. This holistic view reveals the Crab Nebula as a phenomenally efficient energy conversion machine. The central pulsar provides a raw torrent of high-energy particles and radiation. The nebula then acts as a gigantic engine, taking that raw power and processing it through a series of steps: shock heating, magnetic confinement, particle acceleration, and photon scattering, converting it into the vast array of light we see, from radio waves to gamma rays. The unexpected UV excess is a crucial clue in reverse engineering this cosmic engine, highlighting a step in the process that we don't yet fully understand. It reminds us that for all its fame and decades of study, the Crab still holds onto fundamental secrets about the physics of power and light in the aftermath of stellar death. But perhaps one of the most poetic and scientifically profound phenomena surrounding the Crab Nebula isn't a feature of its present state, but a ghost from its past. Scattered throughout the interstellar space around the nebula, astronomers have detected faint, ethereal rings of light that appear to expand outward over time. These are not physical structures, they are illusions of timing known as light echoes. They are the final, delayed photons from the supernova explosion of 1054, having taken a centuries-long detour. Instead of traveling directly toward Earth, this light raced out in other directions, struck distant clouds of interstellar dust, and was reflected toward us, arriving hundreds of years after the main event. We are, in a very real sense, still receiving new light from a star that died a millennium ago. Detecting these incredibly faint echoes is a painstaking task that requires comparing images of the same patch of sky taken years or even decades apart. The process is like a cosmic version of spotting a ripple moving across a vast, dark pond. Astronomers meticulously subtract the static background of stars and galaxies from a modern image, searching for any faint, arc-like feature that wasn't present in an older photograph. When they find one, they can actually measure its rate of expansion. Because light travels at a constant, known speed, the apparent growth of these rings on the sky allows scientists to perform a breathtaking feat of triangulation. By measuring the ring's angular size and knowing the time delay since the explosion, they can calculate the precise distance to the dust cloud that is doing the reflecting, mapping the three-dimensional structure of the interstellar medium around the Crab with astounding accuracy. The true value of these echoes, however, lies not in their geometry but in their spectral fingerprint. When the echo's light is captured and run through a spectrograph, it doesn't show the modern emission lines of the glowing nebula. Instead, it reveals the absorption spectrum of the supernova itself, frozen in time. It is the pristine light of the explosion, a beam that has been perfectly preserved in transit for hundreds of years, allowing us to analyze the chemical composition and physical conditions of the exploding star in its final, cataclysmic moments in a way that historical records never could. This has led to a crucial revelation about the nature of the Crab's progenitor. The light echo spectrum shows the clear signature of a Type II supernova, the explosion of a massive star that had held onto its outer hydrogen envelope until the very end. However, the details within that spectrum suggest the star was not a standard giant. The light shows it was a relatively low-energy event for its type, and that the progenitor star likely had a lower mass than previously assumed, perhaps around 8 to 10 times the mass of our Sun. This helps solve a long-standing puzzle: why the Crab Nebula seems to have less mass than we'd expect from such a brilliant historical supernova. The echo suggests the star had already shed a significant portion of its outer layers into space before it died, creating a dense circumstellar environment that the blast wave would later plow into, which would explain the extraordinary brightness and long duration recorded by ancient astronomers. These faint rings of reflected light are therefore more than just a celestial curiosity. They are a time machine, granting us a second chance to analyze a singular cosmic event and finally understand the life and death of the star that started it all. Yet for all the power and structure these magnetic fields provide, they are far from a serene and orderly framework. Instead, they exist in a state of constant, violent turmoil, twisted into impossibly complex knots and tangles that defy our best simulations. This chaotic magnetic web is not a static cage. It's a dynamic, living entity, and its contortions are the primary reason the Crab Nebula behaves in such unexpectedly energetic ways. Mapping this invisible architecture is one of the greatest challenges in modern astrophysics, and it requires a clever trick. We don't look for the fields directly, but for the subtle fingerprint they leave on the nebula's light. This fingerprint is called polarization, and it acts as a perfect cosmic compass. As those high-speed electrons spiral along magnetic field lines, they don't just emit light, they emit light that is polarized, meaning its electric field vibrates in a preferred direction aligned with the local magnetic field. By meticulously measuring the direction and degree of this polarization across the entire nebula, astronomers can effectively trace the invisible lines of force, creating a detailed map of the magnetic field structure. It's a powerful technique, but the picture it reveals is one of bewildering complexity, not the clean, organized pattern we might expect from a simple spinning magnet. The maps show a field that is profoundly tangled, a chaotic mess of loops and knots where the field strength and direction can change dramatically over astonishingly short distances. Right next to a region of strong, well-ordered field lines, you might find a zone of utter magnetic pandemonium where the field is weak and disorganized. This bizarre inconsistency is the central puzzle. Our standard models, which assume a more gradual and orderly evolution of the field, simply cannot account for such extreme and localized variations. It suggests that powerful, small-scale processes are constantly at work, shredding and rewiring the magnetic fabric of the nebula in real time. The prime suspect for creating this chaos is a combination of the pulsar's powerful wind and the severe turbulence within the expanding nebula. The pulsar doesn't just inject particles, it injects its own magnetic field, which is then carried outward like a rope being unspooled into a raging hurricane. As this wind slams into the slower supernova ejector, it doesn't just create a smooth shock wave, it creates a massively turbulent interface filled with whirlpools and vortices that stretch, fold, and violently reconnect the magnetic field lines. Furthermore, the various components of the nebula are all moving at different speeds, creating shear forces that can twist field lines into knots or even snap them entirely, in events that likely power the mysterious gamma-ray flares. This isn't a peaceful process of inflation. It's a continuous, stormy battle that leaves the magnetic field in a permanently disordered state. Understanding this magnetic maze is absolutely crucial because it is the key to the nebula's most impressive trick. its incredible efficiency as a particle accelerator. The tangled field isn't just a byproduct of the chaos, it is the engine itself. Those twisted lines and turbulent regions are ideal for a process called second-order Fermi acceleration. Imagine an electron as a tiny pinball. In a smooth, regular magnetic field, it would just spiral along uneventfully. But in the crab's turbulent field, it's constantly bouncing off of moving magnetic mirrors, regions of compressed field lines that act like walls rushing toward it. Each collision transfers energy, and over countless encounters, the electron can be boosted to nearly the speed of light. The more tangled the field, the more opportunities there are for these energy-boosting collisions, allowing particles to reach energies that should be impossible in a simpler, calmer system. This deep connection means that by finally deciphering the true three-dimensional structure of the crab's magnetic field, we won't just be solving a local mystery. We will be uncovering the fundamental principles behind nature's most powerful particle accelerators, principles that apply to supernova remnants across the galaxy, to the jets of active black holes, and to other extreme environments throughout the cosmos. The twisted magnetic field is the unseen hand that shapes the visible glory of the Crab Nebula, and each new polarization map brings us closer to understanding its grip. Woven throughout the Crab Nebula's spectacular tapestry of light, the intricate network of filaments tells a story of structure and survival, but this story has unexpected gaps. Scattered among the vibrant, thread-like tendrils are dark, empty regions, voids where the glowing gas simply isn't there. These aren't mere background darkness, they are genuine absences, pockets of nothingness where the nebula's intricate architecture has been erased. Finding these voids is like looking at a beautifully woven rug and discovering several threads have been pulled out, leaving behind holes that question the very integrity of the fabric. Their existence forces us to ask what powerful force could have so completely cleared away material in a system defined by its chaotic density. One leading explanation for these mysterious gaps points to the sheer, brute force of the pulsar wind. While the wind generally energizes the entire nebula, its pressure is not applied evenly across the entire structure. It's more like a fire hose spraying into a cloud of smoke. Some areas receive a direct, concentrated blast, while others are only gently brushed by the outflow. Astronomers theorize that these voids could be regions where the pulsar wind has achieved total domination. In these specific zones, the relentless torrent of particles and radiation may have been so intense and focused that it simply blew the existing filamentary material clean away, preventing new gas from accumulating and creating a permanent bubble of cleared space within the turbulent nebula. An equally compelling possibility involves the violent passage of shock waves. The Crab Nebula is a dynamic environment, crisscrossed by powerful shocks generated by the pulsar wind slamming into slower ejecta and by the ongoing expansion of the entire structure. These shock fronts, moving at incredible speeds, can act like cosmic bulldozers. When a particularly strong shock wave plows through a region, it doesn't just heat the gas and make it glow. It can also accelerate it to such high velocities that the gas effectively evaporates, dissipating into the surrounding volume and becoming too thin and diffuse to detect. The void left behind is the ghostly imprint of that shock's passage, a temporary clearing that might slowly refill over centuries or remain as a permanent scar. The location and shape of these voids offer crucial clues about their origin. If a gap appears aligned with the pulsar's spin axis near the base of its powerful jet, it strongly suggests the clearing was done by the direct, focused output of the central engine. Conversely, a void located along the outer edges of the nebula's expanding shell might be the result of an interaction with the interstellar medium, a dense patch of external material acting like a shield, blocking the expansion of the supernova debris in that particular direction and leaving a relative emptiness behind it. By carefully mapping the distribution of these gaps, astronomers can create a three-dimensional picture of how energy has been distributed and dissipated throughout the nebula's long history. These empty spaces are far more than just curiosities. They are negative imprints of power. Their very absence defines the presence of the immense forces that carved them out. Studying where the nebula isn't provides a unique way to measure the intensity of the pulsar wind and the strength of historical shock waves, offering a complementary perspective to studying the bright structures themselves. Each void is a silent witness to a past cataclysm within the ongoing storm, a frozen record of a moment when the nebula's turbulent equilibrium was decisively broken by a concentrated blast of energy. Yet for all the violent spectacle of light and radiation pouring from the Crab Nebula, some of its most profound secrets are carried by particles that give off no light at all, ghostly messengers that pass through the entire structure and even our planet without a trace. These are neutrinos, and the Crab's extreme environment makes it a prime suspect for producing them in abundance. Neutrinos are among the most elusive fundamental particles in the universe. They are nearly massless, carry no electric charge, and interact so weakly with normal matter that trillions of them pass through your body every second without a single collision. This same property that makes them so hard to detect also makes them uniquely valuable cosmic messengers. Unlike light or charged particles which can be scattered, absorbed, or deflected by magnetic fields on their journey, a neutrino travels in a perfectly straight line from its source, carrying pristine information about the violent event that created it. The Crab Nebula is a compelling candidate source because the processes needed to generate high-energy neutrinos are exactly what it has in abundance: powerful particle acceleration and dense targets. The theory is centered on the interactions within the pulsar wind nebula. Protons and other atomic nuclei, accelerated to near-light speed by the pulsar's fierce winds and shocks, could collide with protons or photons within the dense filaments or the surrounding gas. These catastrophic collisions would produce short-lived particles called pions. When these pions decay, they produce, among other things, gamma rays which we already see in abundance and, crucially, high-energy neutrinos. Detecting a neutrino from the Crab would therefore be a smoking gun, providing direct, incontrovertible proof that hadrons, protons and atomic nuclei, are being accelerated to extreme energies within the nebula, not just electrons. This distinction is vital for solving one of the biggest puzzles in astrophysics, the origin of cosmic rays. We know that atomic nuclei are constantly bombarding Earth from space at incredible energies, but because their paths are bent by galactic magnetic fields, we cannot trace them back to their source. If the Crab is accelerating protons, and we can confirm that with a neutrino detection, it would cement its role as a p-vatron, a natural particle accelerator capable of reaching energies of a peta-electronvolt, 1,000,000 times more energetic than the protons in the Large Hadron Collider. A neutrino would be the unblemished return address on a cosmic ray, pointing directly back to the Crab. The monumental challenge, of course, is actually catching one. Neutrino observatories like the IceCube Neutrino Observatory at the South Pole are engineering marvels designed for this nearly impossible task. IceCube consists of thousands of optical sensors buried deep within a cubic kilometer of pristine Antarctic ice. It doesn't try to catch the neutrino itself, but rather waits for the incredibly rare instance when a high-energy neutrino does interact with an atom in the ice. This collision creates a secondary particle called a muon, which, if moving faster than the speed of light in ice, emits a faint blue shockwave of light known as Cherenkov radiation. IceCube's sensors act like a giant underwater camera, mapping the faint cone of this blue light to reconstruct the energy, and most importantly, the exact direction the original neutrino came from. Despite decades of observation and the Crab's status as a prime target, no high-energy neutrinos have been definitively linked to it yet. This non-detection is in itself a crucial piece of data. It tells us that the Crab's incredible gamma-ray output is likely dominated by electrons via processes like synchrotron radiation and inverse Compton scattering rather than by proton collisions. It places an upper limit on the number of hadrons being accelerated within the nebula, helping to refine our models of its particle population. The hunt continues, however, because a single, unequivocal detection would revolutionize our understanding of its engine. As detectors like IceCube grow more sensitive and analysis techniques more refined, the chance of finally snaring one of these ghostly particles from the Crab increases, promising a direct look into the heart of one of the universe's most powerful natural accelerators. Yet for all our precise measurements of its thousand-year expansion, the Crab Nebula presents us with a curious temporal paradox. If we trace the paths of all those outward streaming filaments backward in time, they converge beautifully around the year 1054, perfectly matching the historical records of the supernova's appearance. This gives us a very confident age of roughly 970 years. But when we look closely at different parts of the nebula, this simple, single age begins to fracture. Various features seem to be moving at different rates, and some structures appear to be evolving on timelines that don't quite align with that neat 970-year clock. It's as if the nebula contains features that are both older and younger than the explosion that created them, a cosmic impossibility that points to a far more complex life story. This age discrepancy isn't an error in measurement, it's a fundamental clue about the environment and history of the nebula. The key to understanding it lies in the fact that the expansion hasn't been a smooth, unhindered glide through a perfect vacuum. Think of it like a crowd of people running out of a building. Initially, everyone might burst out at the same speed, but as they spread into the streets, some will encounter obstacles, a dense crowd to push through, or an open park to sprint across. Their speeds will change relative to one another based on these local conditions. In the Crab Nebula, the obstacles are variations in the density of the interstellar medium and the complex internal pressure from the pulsar wind. Some sections of the nebula's shell are expanding into a region of space that is relatively empty, encountering little resistance. These parts have been able to maintain or even increase their velocity over the centuries. Other sections plowed directly into denser clouds of pre-existing gas and dust. These regions experienced a significant slowdown, like a car driving into a strong headwind. Therefore, the fastest-moving filaments we see today are not necessarily the ones that got the biggest kick from the explosion. They might simply be the ones that had the clearest path. Their current speed suggests a younger dynamical age, but they are just as old as everything else. Conversely, the slowest filaments might appear older and more sedate, but they are actually the veterans that have been fighting the toughest battle against external pressure. The pulsar itself adds another layer of complexity to the age puzzle. Its powerful wind injects energy continuously into the inner regions of the nebula, not just making it glow but actually re-accelerating it. This means the central parts of the nebula have received a second, ongoing boost of energy long after the initial explosion. The expansion there is being actively driven by a modern engine, not just coasting on ancient momentum. This creates a situation where the inner nebula can behave as if it is younger and more dynamic than the outer shell, which is expanding solely on the fading impulse of the original supernova blast wave. We are essentially looking at a system with two different power sources operating on two different timescales, creating a strange hybrid of ages within a single object. Astronomers reconcile these conflicting signals by building sophisticated computer models that simulate not just a single explosion, but centuries of subsequent interaction. They input the known energy of the supernova, the measured power of the pulsar wind, and their best estimates of the surrounding interstellar environment. They then run the simulation for 1,000 years and see if the virtual nebula that results matches the real one in terms of size, shape, and the distribution of velocities. The fact that the Crab's apparent age discrepancies exist is actually a blessing for these modelers. It provides them with critical data points. The differences in expansion rates are the fingerprints of the interstellar medium, allowing them to map the invisible structure of the galaxy around the nebula. The strange vitality of the inner regions precisely quantifies the power output of the pulsar wind. What appears to be a contradiction is actually the key to a far deeper understanding, revealing not just the story of a single star's death, but the ongoing story of its interaction with the galaxy at large. Looking even further into the future, the Crab Nebula's story is one of gradual, inevitable fading, but its final chapter will be written over timescales that dwarf human history. The relentless expansion will continue, its outer filaments pushing ever outward into the interstellar medium, becoming increasingly tenuous and dim. The vibrant colors that define its appearance today, the brilliant reds of hydrogen and the cool blues of doubly ionized oxygen, will slowly dim as the driving force behind them weakens. The central engine, the Crab Pulsar, is also living on borrowed time. It is a spinning top slowly winding down, its incredible rotational energy being bled away with every pulse of radiation and every gust of its powerful wind. Each passing millennium sees it spin a little slower, its furious 30 Hz beat gradually deepening into a slower, more stately rhythm. This spin down has profound consequences for the entire nebula ecosystem. The pulsar's power output is directly tied to its spin rate. As it slows, the wind weakening, the amount of energy flooding into the surrounding nebula decreases. The brilliant inner torus and the shifting X-ray rings will fade first, their intense glow dimming as the particle acceleration at the termination shock becomes less effective. The bizarre gamma-ray flares, those tremendous violations of physics, will become less frequent and less powerful as the magnetic fields that fuel them lose their intensity. The chaotic ballet of the wisps will settle into a slower, more predictable dance, and the sharp, defined structure of features like the anvil will likely soften and dissolve without the constant, focused pressure of the wind to maintain their shape. Within 10,000 years, the visible Crab Nebula will likely have expanded to the point where its surface brightness is too low to easily distinguish from the background sky with the naked eye. It will become a vast, faint ghost of its former self, yet the pulsar will still be there, a fading ember of a once great fire. It will take tens of millions of years for it to slow to a point where it effectively ceases to be a pulsar, its magnetic field too weak to generate significant beams of radiation. It will then become a quiet, inert neutron star silently drifting through the galaxy, a dark monument to its own spectacular past. But even in its old age, the crab will remain an invaluable scientific target. Its long, well-documented life gives astronomers a unique timeline against which to test models of supernova remnant evolution. Watching how its expansion rate changes over centuries will provide exquisite data on the density and structure of the interstellar medium in our galactic neighborhood. The gradual fading of its synchrotron emission across the spectrum will serve as a natural laboratory for studying how relativistic electrons lose their energy over time. And the slow spin down of its pulsar offers a perfect natural experiment in neutron star physics, allowing us to refine our understanding of their interior composition and the nature of superfluid matter under conditions of unimaginable density. Ultimately, the legacy of the Crab Nebula is not just the elements it has scattered into the galaxy, the carbon, oxygen, and iron that will one day be incorporated into new stars and planets. Its true legacy is knowledge. For over 1,000 years from its first recorded sighting to the modern day, it has been a relentless teacher, challenging our assumptions, revealing new physics, and reminding us that the universe is always more complex and wonderful than we can imagine. Long after its visible light has faded from view, the data we have collected from this one object will continue to illuminate the fundamental workings of the cosmos, ensuring that the crab's final whisper will be heard by scientists for generations to come. From its spinning heart to its glowing filaments, the Crab Nebula is a treasure trove of cosmic oddities that challenge and inspire us. We've journeyed through 30 of its strangest phenomena, each revealing a piece of the puzzle about how stars live, die, and leave behind legacies of light and mystery. This isn't just a cloud of dust, it's a dynamic, evolving classroom 6,500 light-years away, teaching us about the laws of physics under conditions we could never replicate on Earth. Every strange glitch, every unexpected flare, and every shimmering filament is a question posed by the universe, pushing us to refine our theories and build better telescopes in pursuit of answers. The story of the crab is a powerful reminder that the universe is not static. It's a place of constant, violent change where even the aftermath of a cataclysm 1,000 years old is still teeming with activity and surprise. What was once considered a settled, well-understood object has repeatedly proven to be a source of profound mystery, from its impossible gamma-ray flares to its missing counter-jet. This celestial wonder shows us that there is always more to discover, always a deeper layer of complexity waiting to be uncovered when we look closely enough with the right tools. It also represents an incredible bridge across time, connecting the meticulous observations of 11th century astronomers to the cutting-edge data from space telescopes today. That thread of human curiosity, stretching from ancient star charts to modern supercomputer simulations, is a testament to our enduring desire to understand our place in the cosmos. The Crab Nebula is a shared inheritance, a cosmic event that has captivated humans for a millennium and will undoubtedly continue to do so for millennia to come. If you enjoyed this deep dive into space's wonders, don't forget to like this video and subscribe to the channel for more journeys to the edge of understanding. Let us know in the comments which of these 30 phenomena bent your mind the most. Was it the nulling pulsar, the mysterious infrared excess, or the sheer violence of those gamma-ray flares? Your thoughts and questions fuel these explorations. Until next time, keep looking